Hello, today we are going to look in more detail at some transformations of complex numbers on our Argand diagrams. So transformations, same as we would have talked about in geometry before, where we're able to move points around or change them, mirror them, things like that. And we're going to look at how that works with complex numbers. First of all, we need to read our complex numbers. So we have Z1 and Z2. Z1 is 4 in the real plus 2 imaginary. So we start at the origin and go plus 4 in the real and then plus 2 in the imaginary. So that's going to be our Z1. And our Z2 we have to read off of our Argand diagram. We start at the origin, we go plus 2 in the real, minus 1 in the imaginary. So 2 real minus 1 imaginary would be minus 1i, or just minus I. Now, when we start to do translations or transformations, like multiplying by 2 or dividing by 2 or multiplying by minus 1, what effect does that have geometrically on our number? So if we have 2 times Z1, we know how to deal with that. We have 2 times 4i, we end up with 8 plus 4i. And if we plot that on our diagram, we start at the origin, go to the real, positive 8, and in the imaginary, we go up 4. This is 2 times Z1. If we take the opposite situation, or kind of the opposite situation where we halved it, we halved our number, we would end up with 2 plus I. So if we go across there, we go 2 plus I would be a half Z1. Now something may jump out at you in this when we draw that in. These are all sitting in a straight line out from the origin. And if I draw in a line to guide the eye, I can see effectively if I have my Z1 and I multiply by 2, I stretch out the modulus of my number. I keep going in the same direction, but I stretch Z1 out away from the origin so that it goes twice as far away from the origin. If I multiply by a half, I squish Z1 and it goes back towards the origin. So it's going in the same direction, going in the same line as we can see, but the modulus gets shrunk or stretched. And linking into another piece of geometry that they might link into in the exam would be to recognize that we have a bunch of similar triangles here. We'd have the same angle going on for each of them, or same angles going on for each of them, but they'd be stretched or squished. So that is a link that could be made, that we have similar triangles going on here. And I'm going to write in some English here. So that's just written in. I have, when I'm multiplying by a number greater than 1, I'm going to end up stretching my number out away from the origin along the same line. And if I multiply by a number that's less than 1, I end up contracting and end up squishing my number back toward the origin along the same line. So my direction doesn't change, but my modulus can get bigger or smaller. I can get stretched or squished. Now what happens if we multiply by minus 1? So far we've been multiplying by positive numbers. What happens when we multiply by minus 1? Well, let's work it out algebraically. And end up with minus 4 minus 2i. So start at the origin and go minus 4 on the real, minus 2 an imaginary. So that would be minus Z1. And what is going on here? Can I see what the relationship is between my Z1 and my minus Z1? Well, there are two different ways you can look at this. Both are equally valid. You can think of this as being rotated through 180 degrees, or often we will look at it more geometrically and say that it has been reflected through the origin. If we started at Z1 and reflected through the origin, through that point, we would end up at minus Z1. So a rotation of 180 degrees counterclockwise or anti-clockwise, or you can think about it as translating through the, or reflecting through the origin. And both will give you the same result. Now what happens if we start multiplying by I or I squared? If we keep multiplying by I over and over again, what effect is that going to have? Well, if I multiply I by this, I'm not going to show my workings here, I'm just going to give you the answers. We'll end up with minus 2 plus 4i. What does that look like? We have minus 2 on the real plus 4i. I is Z1. So we note the positions there, and then we multiply by I squared, and we will end up with minus 4 minus 2i, which we've actually already marked in here, which naturally enough would be the same as multiplying by minus 1. That's also I squared times Z1, I squared being minus 1, so that makes sense. I cubed will give us 2 minus 4i, 2 minus 4i, and Z1. And what happens when we multiply by I to the 4? Well, we might suspect we know what happens when we multiply by I to the 4, because I to the 4 would just be 1. So we would just get our original number back, and we would come back to here, and we would have I to the 4 times Z1. Well, can we note what is happening as we multiply by I each time? We might be able to see that we are going around the origin. We are rotating around the origin by 90 degrees each time. If I draw in my lines now. So if I draw in my blue line here, I can now see it more easily. As I multiply by I each time, I rotate counterclockwise or anti-clockwise around my origin. And this is going to be an important point, this idea that multiplying by I causes a rotation in the anti-clockwise direction is going to be key to the most advanced work we do in complex numbers. I'm going to write in some notes for you here. Now what happens if we multiply two complex numbers by each other, where we have real and imaginary in both things going on? Let's sub in and multiply that out. When we multiply all of that out, 4 on 2 minus I plus 2. So I multiply out all of my parts. This is purely happenstance that I end up with no imaginary parts. So I have minus I plus I is going to sum to 0, and I also have an I squared here, which is going to be minus 1. So I end up with 8 plus 2 is equal to 10. So I end up with a mix of rotation and stretching and contracting. So long as the modulus of my numbers would be greater than 1, I would end up with stretching overall. And my Z1 times Z2 I actually get the real number 10. So I end up collapsing back to the real axis purely by chance. There's no reason to expect this will happen in general. So I get a mix of rotation and stretching. So we get a mixture of rotation and stretching. Now finally, if we're asked about a translation and asked to figure out what that translation was, it means we have if 6 is the translation of Z1 under A plus bi, where a and b are real, find a and b. For those of you comfortable with vector work, this is just the sum of two vectors. So at translation, we know that our complex numbers are effectively vectors. I've kind of mentioned this before. They have a particular direction, and if you add them together, we say we have a translation. So if we add z1 and some other complex number that we need to find the components of, then we are going to end up with 6. So z1 plus some complex number is equal to 6. So z1 translated by this complex number will give us 6. And to find out the translation, we just say, okay, z1 plus this number is 6, and we substitute in what z1 is. That's just going to be 4 plus 2i plus a plus bi is equal to 6. Let's get the stuff we want to find by itself. So isolate our variables as we usually do. Minus 4 minus 2i, minus 4 minus 2i, a plus bi is equal to 2 minus 2i, and then we go back to our old trick. Real is equal to real, imaginary is equal to imaginary, a would be equal to 2, b would be equal to minus 2. So if they talk about a translation of a complex number, it just means we're adding complex numbers